Today's lesson is going to be a little tricky. We're going to talk about motion problems, which pretty much are all word problems, and it's based on the distance formula in algebra. So if you want to find an object's distance, you take the rate at which it's traveling times how long it travels, and that gives you distance. So D will stand for distance, R stands for rate, and T stands for time. So what I did is I looked at a lot of the problems that we have to do, and it seems like there's basically like 4 types of problems for most of the problems that we see that involve 2 objects. So I just kind of named them with based on what they look like they're doing. So the first type of problem is called a catching up, and that's when someone or something leaves before the other. So it might say like John left to go to Florida, and then 2 hours later, Katie left after him. So that's an example of catching up. So when you see this, your setup will be setting the 2 people or 2 objects distances equal to each other. So each one's going to have a distance, and they're going to need to be equal in order to figure out. And it doesn't hurt to sometimes draw a picture of what's happening, and then you can recognize what type of problem it is. So to show catching up, I might show something like this. So someone leaves earlier, they have a head start, and someone leaves later. Working together. So that's when you have either 2 objects or people, they'll either leave in opposite directions or they'll start apart and come together. So to leave in opposite directions, I mean like they travel apart from each other, or they'll travel towards each other. So either way, they're working together to cover a certain distance. And if you see that kind of problem, you're actually going to add their distances together, and that's going to equal whatever total distance is desired. The next type of problem, I call it left in the dust. So that's when someone's faster. So let's say that Olivia and JoJo start running at the same time, but Olivia's faster, so JoJo's going to get left in the dust. So usually you're trying to find how far apart they'll be, so that involves subtraction. And that's going to give you their distance apart. And then last but not least, I just call this problem, it's random. I call it a comparative find. So they'll tell you about like 2 objects doing their own thing. They're both covering a distance. And this one's going this speed for this long, this one's going this speed for this long. So they're not like on the same path, but they're traveling the same distance. That's just going to be like a catching up problem. So you're just going to set the distances equal to each other. And it's kind of hard to draw what that would look like, but basically you'd have 2 separate graphs. So it'd be something like that. It might be someone running to and from somewhere. It's basically the same thing. It's 2 different trips. So the first 2 examples are the easiest. Those are you're talking about one object and you're finding a part of the distance formula. So a car is traveling at this rate for 3 hours, so that's your time. And then you're supposed to find the distance. So distance is rate times time. You're going to put 50 in for the rate, and you're going to put 3 in for the time, for a total of 150 miles. In example 2, this time you're toward the distance and the time it took to get there. So you're finding R. So again, if distance is rate times time, you're going to substitute 220 in for D, and you're going to substitute 4 in for T and leave R alone. So we want to solve this by dividing by 4 on both sides, and we're going to get that our rate is 55 miles per hour. So we're going to do an example of a catching up problem, since that's the first 2-object motion problem we see. So it says, Jose left the airport and traveled towards mountains. Okay, so there is Jose leaving. And then 2.1 hours later, Kayla leaves. So she is starting basically behind him because he has a bit of a head start. He was already up in the air 2.1 hours. So it says after 1.2 hours, Kayla finally catches up to him. So that means she starts out, blah, 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 blah. 1.2 hours, she catches up to him. So you're supposed to find his average speed. So sometimes it helps if we make a chart. Jose's rate is R because we don't know it. And Kayla's is 35 faster. So that means it's 35 plus R. Now, Kayla was only in the air for 1.2 hours. Jose was already in the air 2.1 hours, and then Kayla left, and she caught up to him in 1.2 hours. So he was in the air for a total of 3.3 hours, right? 2.1 hour head start plus the 1.2 it took for her to catch up to him. So when you have a catching up problem, you set each person's distance equal to each other. So I just used kind of D1 for Jose's distance and D2 for Kayla's. And then we substitute. So distance means rate times time. And our rate for Jose is R times 3.3. And for Kayla, we have 35 plus R times 1.2. Notice I put parentheses because I want to do 1.2 times this whole group. And we just kind of go ahead and solve. So we are going to start by multiplying and distributing. So you will get 42 plus 1.2R. And we're going to subtract 1.2. And then we divide by 2.1. So it looks like the rate is going to be 20 miles per hour. So Jose's rate is 20 miles per hour. Okay, so that's the first type of problem. That's the catching up problem. The next problem is a work together problem. We have two cyclists that travel in opposite directions. So right there, the fact that it says opposite directions lets you know it's a work together. And for work togethers, you're going to add up cyclist 1's distance plus cyclist 2's distance for the total length of where are they riding on a trail. So that will equal the total trail length. So they kind of work together to cover a portion. So just to kind of draw a visual, one biker would travel this way. The other would start in the same spot, but they would travel this way. So let's not forget this whole circular trail is 5 miles long. So whatever bike number 1 rides, so going from here to here, and whatever bike number 2 rides, together they make up the whole 5 miles. So that one can be a little tricky. So if I look at my chart, I have my bike 1, bike 2, a rate and a time. So one cyclist is going to travel at 12 miles an hour, the other's at 18. Now we're just looking for when they meet up. So they're both going to be riding the same amount of time. Okay, one's just going to be moving faster, so they're just going to cover more mileage is what's going to happen. But they're still going to be riding for the same amount of time. So we want to go ahead and take 12t and add that to our 18t. And it says the total trail length is 5 miles. And then we're going to solve. All right, so they are going to travel a 1/6 of an hour before they meet. And if you want to know what that is, you would just do 1/6 times 60, and that's going to be 10 minutes. So it's going to take them 10 minutes to meet up. Our next type of problem is what I call the left in the dust problem. So someone's going to start, they're going to start at the same time, and someone's going to pull ahead. So this is where we would subtract to get the distance apart. So Sarah and Morgan are starting to run around track at the same time. Okay, so there goes Sarah. So Sarah's traveling at a rate of 10 miles per hour. Morgan is going 8 miles per hour. So what's going to happen is Morgan's going to go a little slower and she's going to fall further and further behind. So they want to know how long until there's 4.5 miles separating the two of them. Right, so here's Morgan and here's Sarah. I want to know when they'll be 4.5 miles apart. So again, their time is going to be the same. Right, they're both running for the same amount of time. It's just that Sarah's going to cover more distance because she's running at a faster pace. So we want to go ahead and take our 10t and subtract our 8t to get our 4.5 miles apart. And then we go through and solve. So you should get 2.25 hours. That's the same thing as 2 hours and 15 minutes. In case you didn't know, 15 minutes is a quarter of an hour. It's half of a half. So the next problem says an express train travels 80 kilometers per hour from Hoboken to New York City. A local train takes 1.5 hours longer to travel the same distance at 50 kilometers per hour. How far apart are the cities? So basically, we're talking about two different trains. They're both traveling the same distance, but they're going at their own speeds and stuff. So I call this compare to find, but it's set up just like a catching up problem. So we want to know when their distances will be equal or how far apart they're traveling. So an express train is going to be 80 kilometers for T amount of hours. It doesn't say how many hours the first train's going. The second train, however, is traveling 50 miles per hour, and they're going 1.5 hours longer. So longer would indicate we need to add. So we're going to have to write 1.5 plus t for our time. Okay, so the time of the faster moving train, and then time plus 1.5 hours for the second train. Okay, and then we go through and we solve. So when you're finished, you should get that the time that the first train was driving was 2.5 hours. So if you want to know the distance between Hoboken and New York City, all you got to do is put 2.5 in for one of these sides of the equation. It doesn't matter. So I'll just pick 80 because that seems easier. And 80 times 2.5 is going to be 200. And we're talking about kilometers. So that's our distance. So we're going to do 3 problems. These are a little bit tricky. The key is to maybe draw a picture to help us understand and then classify it. So you have 2 trains that leave at the same time. One's going north, the other's going south. So one's going north, the other is going south. So this looks like it's going to be an opposite problem, which means it is a working together. problem. So the first train is going to go 50 miles per hour. Right? We don't know how long it's going to be traveling, so we just write t. And the second train is going 60 miles per hour, and it's going to be traveling for the same amount of time because they're working together to get a certain distance. So we want to know how many hours do they each need to go in order for our mileage to be 275. So the setup for this is going to be addition. So we're going to add 60t plus 50t to make 275. And then we solve for t. So like the first one earlier, we get 2.5 hours. So they'll both be traveling for 2.5 hours to make a total mileage of 275. Letter B, you have two groups of hikers. They start apart and they come together. So they kind of go like this. So anytime they come apart or go away, it is a working together problem. So we'll do WT for working together. And the setup for that is to add the two distances together. All right, so it says that the first group is going 1.5 miles per hour, but it doesn't say how many hours they traveled, so I need to write H. The second group is going 2 miles per hour. And again, we don't know how long they're traveling, but we do know it's the same as the faster group because they're going to meet up. So one group will just cover more of the distance than the other. So we want to go ahead and add our distances. So we're going to add our 2h and our 1.5h. And it says that they started 21 miles apart. So they're working together to cover 21 miles. And then we just go through and solve. So they were walking for 6 hours each. And then letter C, a runner is assigned to run out in the country, so he's going out for a run. Okay, so that's his starting run, and he is going 9 miles per hour. So I'm going to write 9, I'll use T this time instead of H. Okay, because it doesn't tell you how long he's running, so you have to use T. So when he runs out, he's going to get tired, he's going to turn around to come back home, but this time he's only traveling 6 miles per hour. Now, it tells you the whole trip took 2.5 hours, right? That's their total time. So what I would do is take that total time and subtract off the time it took to run that far, right? So if he ran half an hour this way, then he has to have run 2 hours this way because you have to subtract the times. So this one might be a little tricky, but it's actually, I'm just going to call it a comparative time. So even though it's the same runner, he's kind of doing one thing one way and then he's doing something the other way. So irregardless, it's going to have the same setup as a catch-up problem. So we're going to set 9t equal to 6 times 2.5 minus t. And we're just going to solve. Okay, so we find out that the runner was traveling 1 hour the first time he went around. So he was actually traveling 1.5 hours on the way back. Again, probably because he's tired, it's going to take him longer to run. So they're asking you how far did the runner travel first. So now I know t is 1, I can substitute that in and get a total of 9 miles.